Right, Mia, I'm ready whenever you are. Great. Good afternoon, everybody, and welcome to this knowledge exchange forum on thermal energy storage temperature ranges. My name is Emilia Pisani, and I will be the moderator for today. As most of you know, these knowledge exchange forums are a mix between normal webinar and presentations around, with presentations around research and a nerdy discussion with fellow colleagues around a given subject matter. They are informal get-together between interested actors meant for knowledge sharing, awareness raising, and shareholder engagement around thermal energy storage in general and the ThumbsUp solutions in particular. High and low, we look at different contexts so we may better understand the benefits they provide. We highly encourage you to ask questions, comment by using the chat, or simply raising your hand. Heads up, we will record the presentations, but not the discussion. So we pause the recording between each presentation so that there's no right or wrong questions and so that you may feel comfortable participating, engaging, and asking questions. Today, we will discuss how different materials can be used to store different temperatures according to their application. From solar power plants to district heating and cooling to industrial processes, thermal energy storage has been proven to facilitate the integration of renewable energy sources, improve energy efficiency and reliability of energy systems. Store temperatures can range from minus 150 degrees Celsius using cryogenic fluids such as liquid nitrogen or liquid air, up to 1,400 Celsius using molten salts or rocks, sand or ceramics. There's a great spectrum of materials, temperatures, applications, and technology readiness levels. So that means from when it's just an idea in the lab to when it's market ready and ready to be sold and rolled out. And these need to be considered. Since the solutions being developed by the ThumbsUp project are designed for residential buildings and aim to store between 25 to 150 degrees, the plain vanilla of thermal energy storage, we wanted to expand our horizons and learn more about the different possibilities and application of these energy storage systems. Today, we have the pleasure of collaborating with the LoCoMoSa project to learn more about how molten salt can be used for long-term storage in industrial processes. The LoCoMoSa stands for low-cost molten salt thermal energy storage for industrial processes. And to learn more about this fascinating project, I would like to give a warm welcome to Dr. Julius Weiss, research at Fraunhofer ISC, specialized in climate neutral industrial processes and high temperature storage. He just finished his PhD this summer. So congratulations, Julius, and thank you for joining us. On behalf of the ThumbsUp project, I'm joined by my colleagues Antonio Foita, material scientist at the National Research Council of Italy, who specializes in the synthesis and characterization of composite materials based on hydrated salts for thermochemical energy storage. He is passionate about optimizing material performance for innovative energy storage solution, as well as Meishi Liu, research fellow at Birmingham Center for Energy Storage at University of Birmingham. Her research interests focus on thermal energy processes and systems including thermal energy, heat and cold storage, and system simulation and optimization. Last but not least, here to help out is my colleague Ulla Gustafsson, project manager and research institutes of Sweden, specialized in energy systems and heating technologies, who will be my collaborator for the day. So these two projects are very different, but they both aim to develop efficient low-cost thermal energy storage, though with different components, uses, and applications. Having said that, without further ado, please welcome Julius. Thank you for being here with us today. And can you please tell us a little bit more about the work you're doing in the LoCoMoSa project?
Yeah, I hope I can show you a bit more. I'm going to share my presentation so I can okay.
You should be able to share it now.
No, I should be able to share it. I'm going to share my presentation so it's easier to have a nice continuous flow of the slides. And let me get my notes on this screen. Okay. Yeah. Yeah, thanks again for the kind introduction. As mentioned, I'm here to represent the LoCoMoSa project consortium. And as the technology of molten salt storage and the ThumbsUp technologies are pretty different. The idea was to basically maybe give an overview about relevant thermal storage technologies and grouping them by temperature ranges and put them into relation. And this is what I'm trying to do today. But before, I'm going to give you a small introduction into the LoCoMoSa project and why we're doing this project. And afterwards, then the rest of the storage technologies will be put into relation afterwards. So LoCoMoSa project is about decarbonizing industrial processes or industrial heat. When we look at the share of heat on industrial processes, it's 3/4 of the industrial energy demand is for heat. And still most of it is fed by fossil fuels today. So on the one hand side, we need to have more energy efficient consumption of this energy, and we have to have a recovery of waste heat. And on the other hand, we need to move to a transition to low cost, zero carbon supply of this energy for or heat demand. And in parallel, we have to make sure that we have security of supply and predictable cost of this heat. And this is what we try to address with LoCoMoSa. So it's obvious with moving away from fossil fuels in future, most of this heat will be electrified in the end. And when we look at, here's an example for the electricity prices in Germany. You can see the prices in red, and this is a week in April, and in green we can see the renewable energy generation. And we see that we have these periods of very low electricity prices or even negative electricity prices. And then there's these periods with high electricity prices. So if we want to fulfill our heat demand with electricity, the first thought is, if I have a battery, I can manage this, this balance and fulfill my demand with a battery. But nevertheless, that the cost of battery was massively decreasing in the last years. The cost of battery is still way higher than the cost of thermal storage system as we know them from CSP power plants, for example. And we have a limited lifetime of these batteries and cycle stability. So we have a real cost advantage of the thermal storage. And this is why we plan on to bring these thermal storages from CSP power plants into industrial sites. So what's the benefits is that we can have low cost renewable electricity to be utilized for heat generation during periods of low cost. And then we have the power to heat system where we produce heat out of electricity, and we have a conversion of almost 100% here on this side with an electrical resistance heater. And the thermal storage is essential for balancing then the variable heat demand and not necessarily matching low price periods of electricity. How to integrate such a system? So we have this electrical heater, and then we have a heat transfer fluid that we push into the heater. We store it in a hot tank. Then we can produce steam for an industrial site on demand. When producing the steam, our heat transfer fluid is cooled down, stored in a cold tank, and then we can start over this process again. So this is pretty simple and straightforward so far. In the LoCoMoSa project, we look at some specific parts of this. So this is a consortium out of 6 partners, 3 out of Denmark, 2 out of Denmark, 2 out of Germany, and 2 out of Italy. Exactly. So the main objective is to demonstrate a low-cost molten salt thermal energy storage, as Emilia already introduced to you. And some specific objectives is, on the one hand side, we look into an electrical heater that has a medium voltage electric energy supply. And by this, we can save costs for the system overall and improve the efficiency of the system even further. And on the other hand, we demonstrate an adaptive bed factor heat exchanger or steam generator with a novel heat transfer geometry. So this is the part that the Italian partners have. And yeah, overall aim is of the whole system as such to reduce the capex and the opex costs through system level optimization and operational strategies. So this was the introduction into the LoCoMoSa project. Now we move to this other part of the presentation with the temperature ranges. So sticking to the molten salt system, these are known from solar thermal power plants and installed in, can I move this? Yeah. In very large capacities. So several tens of thousands tons of salt are used in each plant, and we have storage capacities in the gigawatt hour range. And the idea is to bring this into industrial applications from the CSP power plants in the LoCoMoSa project. The question is, when we look into other technologies, is then still molten salt interesting? There's a nice overview about different suppliers of high temperature storage suppliers. There's a multitude of suppliers worldwide on the market for high temperature storage. And we have but a bit of missing commercial plants in operation. So only 6 of them are in operation. And we can see that most of these suppliers, or share of 50%, is coming from the European region. And what we can see here is the green suppliers are the ones with the commercial system in the market. And now when we look at this, why do we have such a wide temperature range? So this is not possible with molten salt, but with different other materials. So we have a variety of plenty different materials coming from crushed rock, molten salt, and then ceramics, concrete, sand, silicon, ceramic bricks, graphite. And we cannot see any material that is winning this race, but all of these materials have their specific application, and then it's not the standard project, but somehow that needs to fit the process and the application and the temperature ranges and also itself. And on the other hand, besides these solid storage materials, we have all different kind of heat transfer fluids that go in hand with this solid materials. So we have water and steam, we have lots of air systems, some of them work with flue gases, then there's obviously molten salt systems into it, and this classical better known thermal oil storage systems, as well as inert gases for operating the systems depending on the temperature level. Exactly. Now, if we go into the more commercial application and decrease our temperatures coming to 200 degrees, what we see a lot in the market already in commercial applications is this pressurized water systems where we can store temperatures up to 200 degrees. And we have a bit of pressure on this cans, basically. So it's really thin steel walls like a soda can, but a bit higher, a bit bigger, and a bit of pressure inside. So we have volumes of 6,000 cubic meters. And for these systems, we need to have an expansion vessel for compensating the expansion of the water. Systems are built up to 850 megawatt hours are installed. Yeah. If we lower our temperature range, then we are at pressureless water systems. So all of we nowadays see lots of these tanks, at least in Germany, to be installed, also combined with a power to heat system most of the time for periods of excess energy or low price electricity. Somehow similar to the LoCoMoSa system, but for lower temperature and for district heating. So we have also huge tanks, about 1,000 cubic meters, or even larger systems we can see in these pit storage types systems, which we do not have too much in Germany, but in Denmark, for example, we can see them a lot. And then there's also borehole aquifer systems. Yeah. So there's different aspects when designing these tanks as the surface to volume ratio. And in this pressureless systems, we have a bit better volume to surface ratio. We have less heat loss compared to this pressurized systems. And the application for these systems I already mentioned. Most of the time it's district heating, district cooling. Exactly. If we go further down in the temperature range, we're moving more in towards the direction of the ThumbsUp project. So coming to phase change material, and the cheapest storage material obvious is water. So we have storage volumes up to 1,700 cubic meters and capacities of 160 megawatt hours for these systems in operation. The main problem with PCM materials is the limitation of the thermal conductivity in the solid material when it's frozen, the water. And there's different ideas how to counteract this with heat exchangers and detaching of the ice surface or encapsulating the PCM materials. All of this has its pros and cons, increasing costs, and complexity of the system, but all different kind of ideas are found in literature. And we have these applications is for food, building, industrial cooling, where we can find the systems. And then coming to the last temperature range, this is something really specific. The other things were more general, but here this is something specific that we also do on our institute, is this phase change slurry materials. So having a slurry that is pumpable from one tank to another tank, having the benefits of a pure liquid system and of a phase change material combined. So we are looking into two systems. One is the combination of water plus oil for phase change slurries below 0 degrees as a temperature range. So we have a storage capacity that's 3.5 times higher compared to if we would use pure oil. Here we do not have too much long duration tests, so we need to further investigate the cycle stability and the subcooling effect of the systems. But what we really investigated a lot is the oil in water phase change slurries, where we can have operate in temperatures between 12 to 60 degrees. And here we have a storage capacity that is 3 times higher compared to pure water systems. We have lots of cycle proven, and we also have demonstration in a scale of 7,000 liters in a domestic heating application plant. Exactly. So wrapping up the temperature ranges, once again, we were coming from this molten salt systems. Molten salt itself, for the LoCoMoSa project, we look into temperatures between 290 to 550 degrees, but depending on the salt mixture, we can also go to lower temperatures or to higher temperatures. The higher the temperature, the more corrosive the salt, the more problematic, I would summarize. Lower temperatures is somehow possible, but then we are also in direct comparison to water-based systems, which are cheaper. So that's also a difficult business case. Speaking of water, as mentioned, there's the temperature range of using water or steam from 0 to a bit up to a bit more than 200 degrees. We can directly store in water, steam. Then there's these solid materials, rock, sand, ceramics, which you can see different storage manufacturers addressing different temperature ranges. Then we can also find in reality that increasing in temperature comes with increasing in cost. So this is not for free. Yeah, and then talking about bulk PCM materials, I would give this part to ThumbsUp project, but compared in the temperature range, we can also, when working with different material classes, as again, we could also work with salts. We can go up to 350 degrees with this. And then there is this phase change slurries, a bit of a special topic that I mentioned with the given temperature range, and then the classical thermal oil storage systems that are historic-wise already in the systems, in a few systems, let's say. Exactly. So that's in a nutshell the whole temperature range of storage technologies. And with this, I thank you for your attention and for the funding for this project, LoCoMoSa project. And I'm looking for hopefully fruitful, interesting discussion afterwards.
Thank you very much. And I believe we can start the recording again.
Okay, thank you, Emilia, for the introduction. Yes, I work in ThumbsUp project in the part of sorption material using thermochemical materials for thermal energy storage. So just a briefly introduction about the ThumbsUp project is ThumbsUp is the acronym of thermal energy storage solution to optimally manage buildings and unlock their grid balancing and flexibility potential. It's better ThumbsUp as a name. Then the project is structured in 3 phases. Now is we are in at the final of the phase 2, maybe in the phase 3. So the phase 1 is enabling technologies development. The phase 2 is the validation and the demonstration campaigns, and the phase 3 is the replication campaign. The ThumbsUp consortium. In the ThumbsUp consortium, there are 19 partners for 9 countries. And more in particular, the 3 phases of this project is the first phase is to develop 2 kinds of prototype, fractless that we will talk with the other colleague, based on PCM, and sorters that we develop with CNR, Unime, for the material part and other partners. The second phase is the validation of this prototype with the help of Cartif, that is in Spain, the building for the test. And then the demonstration, we have 3 buildings for the demonstration, one in Sweden at Gothenburg, 2 in Valladolid in Spain, just to see the application of this prototype in 2 different climate zones, and just to see how to work with for heat and cooling, and with the interaction with the district heating. And then the third phase, the replication of this campaign in order to study in another building the impact of this solution. In particular, this study will be dedicated of the impact of district heating network and electric grid level. So, how do a thermochemical test work? In general, there are this is the reaction that we start with a compound A to obtain 2 different compounds, B and C. A and B usually are a solid compound or liquid, and C is a volatile compound. In the case of the ThumbsUp project, C is a water, A is a composite material that absorbs the water, and B is the dry composite material. So this material, this reaction is structured in 3 phases. Heat storage charging reaction. So we have an endothermic reaction leading to formation of B and C separately. Heat storage period where B and C are kept separated in order to avoid the recombination reaction, and this heat storage discharging reaction that is an exothermic reaction between B and C, which allow to extract heat from the storage system. In particular, just to see the temperature range of the TCM, in our case, we have absorption materials. So for the phase of charging, we have a range of temperature between 150 Celsius degree to 80 degree, more or less. But while the discharge phase, the range of temperature of discharge is between 50 degree and 10 degree. How do absorption tests work for heat and cold storage? During the charging phase, we supply heat at the absorbent material. That's the pair we see in the previous slide, the absorbent and the vapor. The vapor go to a condenser that change in between the vapor to the liquid and release it to the ambient. Then we have the heat stored, and then the discharging phase. During the discharging phase, we have two effects: cooling effect and heating effect. Cooling effect because the ambient supply heat to the liquid in order to evaporate the water. The water transforms in vapor that the absorbent material absorb this vapor and release heat to heating, for example, water or the ambient of the building. Desorption storage materials can be desorption storage can be classified in solid sorption, liquid sorption. In particular, solid sorption can be divided in other two categories: chemical reaction and solid absorption. An example of liquid absorption is a concentrated solution of salt, for example, lithium chloride, magnesium chloride, or calcium chloride. For another example for solid absorption, composite material, that is the case of the ThumbsUp solution. In particular, in the ThumbsUp project, we used a composite based on using a porous matrix as a porous matrix silica gel and impregnated with calcium chloride. Here there are an example of operating temperature in our absorption test. We can see in this graph the charging phase. The range of temperature is between 110 Celsius degree and 25 degree during the charging phase. In this part of the graph, we can see the inlet humidity. It is constant at 4, and the outlet humidity that this humidity is released by the water absorbed in the material. In the discharging phase, we can see this other range of temperature between 40 and 20, and this is the heating of this reaction. This is another example. In this case, is a closed absorption test. And just to see the range of temperature, this is the temperature of the evaporator, where this line is the inlet temperature of the evaporator, more or less 12 Celsius degree, and the dotted line is the temperature out of the evaporator. Here we have the temperature of the absorber, just to see the range of temperature. The range of temperature of this application is between more or less 45 degree and 55 degree. Here there are another example of closed absorption test. It's important to see that it's possible in the same time with this system to cooling and heating, because when we heating it's possible to see the two different parts of absorption and desorption. And just to finish my presentation, this is another project that we work, Cybergrid project, just to see that more or less it's the same range temperature of application. And in this case, it's possible to connect this prototype with, for example, a district heating or the fourth generation of district heating. So thank you for the attention, and if we have a question.
Okay.
And I guess we start recording.
Okay. Okay, hello everyone. Thank you so much for inviting me for this forum. And I'm Macy. I'm currently working in Birmingham Center for Energy Storage at University of Birmingham. And before I start, I will firstly briefly introduce our center. So we are based in University of Birmingham, and our center is called Birmingham Center for Energy Storage, and our research mainly focus on the thermal energy storage system, including the material development and the whole system design, optimization, and like fundamental research on the heat fluid. Also, we do something like the energy policy. And we have very good researchers in our group. So if you are interested in collaboration, you can find like our details in this website here. And now we can move to the our project. As you can see that we are focused on the thermal energy storage units. So this is also the topic of our project ThumbsUp focus on. So I will give you an overview of our project. So we aim to develop thermal energy storage units from one is daily uses, and the other is like long duration uses to integrate the TES units to the buildings and to provide like heating and cooling to the residents. And so why this energy storage matters? The main reasons is like shown in this diagram here. So you can see that the heating and the cooling is the largest source of the energy demand, and the carbon dioxide emissions in Europe, with the residential sector accounting for 45% of the final heating and cooling consumption. And now they still mainly rely on the fossil fuels. So we want to use the renewable energy resources like the heat pumps and the solar and geothermal, so to apply in the buildings. That's why we want to develop the thermal energy storage units to integrate with the building and to provide a flexible operation of the resources with the TS units. In general, we have like 3 ways to store the heat. One is sensible, one is latent, and one is thermochemical. And the thermochemical one is already introduced by Antonio. So we focus is on the latent heat energy storage unit, which uses a phase change material here. And this latent heat thermal energy storage is one solution for the ThumbsUp for the short durations. And we are designing this unit now, and it has 3 components. One is heat transfer fluid, one is heat exchanger, and the other is PCM. So the heat transfer fluid is a working fluid in the system, provide heat or cold energy. And we always use like water, air, or oil, gas, like these things, fluid. And the heat exchanger is what us UOB are doing now. which will transfer the heat to or from the PCM. And there are many kinds of heat exchanger in the market now, the shell and tube, thin tube, and plate exchanger. And we are focusing on the plate exchanger now, and I will introduce a bit later. Then the PCM is the core material to store and release the latent heat energy from the unit. And now I will introduce this part first. So what is the phase change material? It is a material that can absorb or release the latent heat when they change their phases. For example, the ice, when they are at 0 degrees, they are like solid phase. But if they release the latent heat, they can change to the water also at 0 degrees. And this latent heat is around 300 kilojoules per kilogram. So it's a lot of like energy we can use. And also during the phase change, the temperature is quite stable at this stage here. So that's why we think the phase changer material is a very good material for thermal energy storage. Now let's see the types of the phase changer material. So considering the chemical component, it has 3 different types here. One is organic, like paraffin, fatty acids, alcohol, and ester. And they usually have a quite good chemical stability and non-corrosive, but they usually have quite low thermal conductivity. And the second type is inorganic, like the metal alloys and hydrate and the molten salt. And they have higher latent heat values and better thermal conductivity. But some of them have some issues like phase separation or supercooling. And the third type is eutectic mixtures. This type is a kind of a mixture of 2 or more components to create a material together with a quite sharp melting point. And they also, but they have a good thermal balance. From the ThumbsUp project, we are focusing on the organic one. Then let's see the temperature range of the PCM. From the application, PCM can be used in a wide range of applications from the temperature, like minus to like 1000 degrees. So here I use a diagram to show like how the PCM range varies from this temperature. Like the low temperature, we use for less 100 degrees, and we usually use it for building heating and cooling. And for the medium one, for example, the sugar alcohols here, they have a melting temperature from 100 to 200 degrees, and they usually use for solar applications. And for the high temperature, for more than 200 degrees, they usually use for waste heat recovery in the industrial. So in the ThumbsUp, what we are focused on is bio-based PCM. So bio-based PCM is a kind of organic PCM. They are originally from like natural or renewable sources like plants or fats like meats and oils. And their temperature range varies from -80 to 275 degrees, which is quite narrow. But they have a quite also higher latent heat values from 10 to 350 kilojoules per kilogram. So because it's organic, so they are quite renewable and environmentally and non-toxic, but also they have quite lower thermal conductivity, which brings us big challenges for thermal energy storage systems, because we want sometimes we want to be better heat transfer. Then that brings us a question like how to select the PCM. So when we need to choose a PCM, we don't usually say which PCM we can use. We usually ask us questions like, firstly is what temperature range we need. So then we will say then we will find what phase change temperature you need, and what is the final user requirement, like the outlet temperature the final users needed. For example, for the heating and cooling in the buildings, for heating, for the shower, we probably need 50 degrees, and for cooling, air condition, probably we need 20 degrees. So we have to consider these to select the PCM. And second is we have to consider how much the energy storage capacity is required. And then we need to think if we need to select high density of the PCM and the larger and large heat capacity. And third is if it's chemically stable and safe for long-term use, because when we use a PCM, we want to be long-term uses and not just a few weeks, because some PCM's performance will change after a few cycles. So we have to know what is our needs here. And the fourth is if this PCM is compatible with containers. So some PCM will have reaction or corrosion with the container. So we have to be careful about this. And the last is the cost and availability. So cost is always our first thing to think if the PCM is costly and easy availability. And then in summarize that the PCM could provide a very good thermal energy storage characters, improve the energy efficiency, and it can provide stable temperature. But it also have big challenges for our research, its low conductivity and the price. So that's why we are researching on this. From here, you can see in our real life, you might have already used a PCM without realizing it. For example, the transportation for the vaccine and clinical industries, and even the food deliveries. So yeah, we are living with it now. And now I will come to the other components of the our latent heat thermal energy storage unit is a heat exchanger. So in the past, we have investigated a lot in the heat exchanger design. For example, in the past, we have explored how is the fin to heat exchanger, how many fins and the fins configuration can affect the thermal energy storage unit. And now we are investigating the plate type heat exchanger. So we are optimizing the channel on the plate, here, how could we optimize the topology to improve the heat transfer, because the PCM we are using has a quite low thermal conductivity. So we are finding the balance between these two. So yeah, so to wrap up, PCM is quite efficient thermal energy storage across the diverse sectors, and but we are still facing some challenges, and we are working together to fix this out in the ThumbsUp project. And hopefully in the future, we could share these investigations with all of you here. Yeah, thank you.